Let's talk about how proportionality can be applied to other aspects of triangles, and even to diagrams outside of triangles, like the one you see on your screen now. First, let's learn the Triangle Proportionality Theorem, which states that if there is a line that is parallel to one of the sides of a triangle, like how XY is parallel to BC, and that line intersects the other two sides of the triangle, like how XY intersects side AB and side AC, then this line, XY, divided those two sides of the triangle proportionally. So since XY is parallel to one of the sides of the triangle, we would know that AX over XB is equal to AY over YC. And we also have the triangle proportionality converse, which says the same thing but in reverse. If a line divides two sides of a triangle proportionally, so this isn't a real notation, it's something I made up that you put basically the symbol for similarity, the little squiggle. Instead of the straight congruence marks, you use squiggle marks to denote that they're proportional. I think it works. Feel free to use it if you want to. But anyway, this diagram is showing us that AX over XB is equal to AY over YC. So since XY divided the two sides of this triangle proportionally, XY must be parallel to BC. We can extend the idea of the triangle proportionality theorem and its converse to a diagram that looks like this, which at first glance might not look like a triangle, but it would be eventually, right? Line D and line E aren't parallel. Eventually they would intersect to form a big old triangle. So we just have multiple parallel lines inside of that triangle. And that's basically all that this theorem says, is that if three or more parallel lines are cut by two transversals, and these transversals are really like the sides of the triangles that we saw in the previous two theorems, then the transversals have been divided proportionally. So since lines A, B, and C are parallel, we can tell that PQ over QR is equal to ST over TU. In other words, the way that segment PR was divided by line B is proportional to the way segment SU was divided by line B. So let's put these theorems into practice. Here I see a triangle that has a line inside of it that's parallel to one of the sides of the triangle. According to the Triangle Proportionality Theorem, we know that line ST divided side PR and side QR proportionally. So I can set up a ratio that looks like this: PS over 42, so that's the way that segment PR was divided, is equal to 48 over 36, because that's the way that segment QR was divided. To solve, we'll just cross multiply. So 36 times PS is equal to 42 times 48, which is 2016. Divide both sides by 36, and we find out that the length of PS must be 56 inches. For our next problem, we're going to want to use the triangle proportionality converse, because this time we know the way that these two sides have been divided. We know all four of the lengths. What we don't know is whether PQ is parallel to ST or not. In order to show that ST is parallel to PQ, we must show that side PR and side QR were divided proportionally by ST. So let's set up our ratio of 27 over 12. That's the way that side PR was divided. And set that equal to 36 over 16. That's the way that segment QR was divided. Then we can reduce each of those fractions. 27 and 12 are both divisible by 3, so I get 9/4. And 36 and 16 are both divisible by 4, so again I get 9/4. Since I got the same ratio when I reduced my side lengths, I can tell that side PQ must be parallel to line ST by the triangle proportionality converse. In our final example, we have three parallel lines cut by two transversals. Since the lines are parallel, I know that the transversals have been cut proportionally. So I can say that 75 over 165, that's the way the top transversal was cut, is equal to FG over 154. That's the way the bottom transversal is cut. And I can cross multiply to solve. 75 times 154 is 11,550. Divide that by 165, and we find out that the length of FG is 70 meters. And that's the basics of what you need to know about the triangle proportionality theorem, its converse, and the proportional parts of parallel lines theorem. In our next lesson, we'll talk about how we can apply these theorems to real-world problems.